In this video, we're going to look at several more examples of alkylation and acylation reactions. So here's three reactions that we will work through. Notice that we are starting with benzene in each case, and all of the other reactants are alkyl halides. So these are going to be alkylation reactions. A few things to remember with alkylation. There is always the possibility and likelihood of multiple additions. So you're going to get more than one alkyl group to add to the benzene ring. And unless otherwise stated in the problem, assume that you are only going to add once, even though if you were to actually do this in the lab, it will likely add more than once. Another thing that's possible with alkylation is the rearrangement of the carbocation that's formed. And this is something that you always need to think about. If it's possible to rearrange to a more stable carbocation, it will before it adds to the benzene ring. So let's take a look at each of these examples. So the first thing that I suggest you do is determine what the carbocation is that will form. And that carbocation comes from the alkyl halide. So essentially what we need to do is remove the halogen. So here's the alkyl halide we're starting with. So the carbocation comes from the loss of the halogen, and then the carbon that halogen was attached to is now your carbocation. So notice in this specific example that carbocation is a primary carbocation because the carbon that the positive charge is attached to only one other carbon. Now primary carbocations are technically not stable enough to form. Here they will form because it's not actually just a carbocation, it's a complex along with the aluminum chloride. However, once the primary carbocation forms, it will rearrange. So notice that we do have a hydrogen adjacent to the carbocation. So what's going to happen is we will get a hydride shift, and now we will form a tertiary carbocation. So that hydrogen shifts down to where the carbocation was, leaving the previous carbon that it was attached to with the positive charge. Now we have a tertiary carbocation, which is very stable. So that carbon that now has the carbocation is going to be what gets attached to the benzene ring. So if we draw our benzene, and because here it's an unsubstituted benzene, it doesn't really matter where we actually attach it. So this carbon is now that one with the carbocation. So at this point, you just need to make sure that you have the right number of total carbons. So I'm going to draw 2, 3, so 2, 3. And then that first one that's attached to the ring has two other methyl groups coming off of it. So there is your final product. If we look at the next example, again, we first need to determine our carbocation. So here's the alkyl halide that we're starting with. We're going to erase the halogen, and that is where our carbocation is located. We have hydrogens to the right, and we have methyl groups to the left of the carbocation. If I were to do a hydride shift from that right carbon, it would form a primary carbocation, which does not help because where I'm starting is secondary. So instead, what we're going to do is a methyl shift. So the methyl group is going to shift over. And what we now have is one methyl group on that second carbon. We now have one on the third, and that carbocation is where the methyl group came from. So again, now this is the carbon that is going to attach to the benzene ring. That carbon has, again, two methyl groups coming off of it. Then I've got two more carbons and another methyl group coming off of that second carbon. So there's your product for the second reaction. Third example here. This time we actually have two halogens, and you're only going to remove one at a time. So let's take a look here. That's where we're starting. Both of these halogens are equivalent in that they're going to produce a secondary carbocation. So I'm just going to get rid of one of them first. There's the carbocation that forms, and I can't make it any more stable than secondary. If I shift over one to the left, it's still secondary, If I shift over to the right, it would become primary. So I'm at the most stable carbocation. So if I attach that to the ring, so we're attaching to this carbon, I'll have a methyl group, and then I'll also have 1, 2, 3, 4 more carbons. And the second to the last is going to have a bromine. So now I still have an alkyl halide in the mix here. So what's going to happen is if this chain is long enough, I'm going to close and form a second ring here. And notice what I will have. I have 1, 2, 3, 4, 5, 6 carbons that I can form a 6-membered ring. So if you have 5 or more, that ring can form. Anything smaller is not likely to form because there's not enough bend in your structure. So I'm going to form a new carbocation. I'm going to get rid of this halogen. So there's where the carbocation is formed. So I'm now going to form a bond between that carbon and the next carbon down on the benzene ring. So I still have the benzene. And again, like I said, I have those 6 carbons to make a 6-membered ring. I still have this methyl group coming off of what's now the top of that ring. And I'm going to also have a methyl group coming off of the bottom of that ring. So there would be your product for this last example. Here's 3 more, and in these examples we have acylation reactions because what we're starting with is an acyl chloride. So in these examples, what you're going to do is again remove the halogen and attach the benzene to that same carbon. With acylation, you do not have to worry about multiple addition because what you're doing is adding an electron withdrawing group, and acylation and alkylation technically don't react any further once there's an electron withdrawing group on the ring. You also don't have a rearrangement because the carbocation that forms is already resonance stabilized, so there's really no way to make anything more stable. So you've got really less things to worry about with the acylation. So if I get rid of the halogen, that is now the carbocation. So that carbon is what's going to attach to the benzene ring. So we're going to have the double bond to oxygen. And then again, you just have to make sure you're attaching the right number of carbons in the right way. So I'm going to have 3 with the methyl coming off of that first one. So there would be your product of this first acylation example. You're going to end up with ketone groups attached to your benzene ring essentially. Second example here, again, we will get rid of the halogen. Oops. Form our carbocation, and that's where we will attach to the ring. And in this example, we just have a kind of a linear ketone here. So there's your product for the second example. Third example, much like the previous third one with the alkylation, notice we now have 2 halides. So we're going to remove one first. Again, they're equivalent, being on the ends of this chain here. So there's the first carbocation. So if I attach that to the ring, I've got 1, 2, 3, 4 plus the chlorine. So there's the first step. Now in the previous alkylation example, we were able to close that ring because we do get multiple reactions to happen. Remember I said a few minutes ago with acylation, you do not get multiple additions because this right here is electron withdrawing and it's deactivating the ring. So this is actually the final product. Even though you have a nice 6-membered ring possibility here like we did in the previous example, it's not going to close that ring. This is where you are left. So let's now do kind of retrosynthetic analysis on what could be an acylation or alkylation product. So I have benzene, and notice I do have an alkyl group attached. So there's no carbon-oxygen double bond, so this is just an alkyl group. So this would, as far as we know now, need to come from an alkylation. So if I work my way backwards, I'm going to break that carbon-carbon bond right at the benzene ring. So I would need benzene. And then the alkyl group that was attached would look like this. Remember, this would have to come from a carbocation. And that carbocation would have to be on the carbon that's being attached directly to the benzene ring. So this is what that carbocation would look like. Notice that this is a primary carbocation. And when we talked about alkylation, we said if it's possible to rearrange, it will. And notice there is a hydride right next door. So this primary carbocation is not going to actually be the one available to react to give this product. So this won't work. Okay, so one reaction we have not yet talked about is the ability to do an acylation and then reduce that product into an alkyl group. And that's what's actually done here. So I wanted to show this example just so you're aware of that. So when we look at that reduction example, you'll remember this. So really what this is going to come from is benzene and then the corresponding acyl group, so the acyl chloride. So that would be your two starting materials. So the intermediate that's formed would look like this. That you should be able to recognize as something we've been doing now. What we have not done yet then is the reduction of that acyl group into the alkyl group. And we will talk about that in a later video. But this is possible. So if you have the need to add a primary carbon directly to your benzene, it is possible by first doing acylation and then a reduction.